Hello and welcome to Open Logic. In this video, we're going to look at writing simple directed test. Previously, we have studied a serializer design. We've seen the design code and we've understood its behavior. Now, writing test is to actualize the behavior and to confirm that the design intent is achieved. I've got to say, writing test is a bit of an art. There are many ways to write code. Some coding style offers convenience, some offers readability. Some offers short-term advantage and some offers longer-term advantage. We'll get to see some of them later. Without further ado, let's get started. We can start with a top-level module. There are 4 areas we need to deal with. First one is to create a bunch of wires, and then we instantiate the design. Using the wires, we can control the design inputs and we can monitor the design outputs. Now let's look at it one by one. First, the wires. That's kinda simple. We just create a bunch of wires or logic. These are to be connected to the design port. Second, we instantiate the design. These are design ports and these are the wires we created. If you pay attention, I have added prefix W to declare the wires. You can actually use the original port names as in the design without the prefix. If you do so, this is how the code looks like. This code is not wrong, definitely, but the beginner may get confused on how to read the code. What is this iClock with the dot and what is this iClock in the bracket? With the prefix, it's easier to guess that these are the design ports and these are the top level wires. However, using the same name will allow you to use a shortcut, which is dot star. This basically means the top level module has all the wires which are named exactly like the design port, so you don't have to write the port connection one by one. Personally, I'm not a fan of this coding style because sometimes I'm trying to see how a wire is connected. When I read the file and search for, let's say, iClock, I will only find it here, and therefore I would jump to conclusion that iClock is not being used at all, because I couldn't find it anywhere else in the file, which is not true in this case. So we need to constantly remember how a wire can be connected through this dot star mechanism. Either this or write down all the port connections for clarity purpose. For this video, we'll continue to use these wires. Now controlling input. There are several things we need to do. The most important one is to generate a clock. Say if we want to generate a 10 nanosecond period clock, this is the simplest way to do it. On every 5 nanoseconds, the signal WI clock toggles between 1 and 0. However, this code doesn't work. Can you tell why? That's because WI clock is a logic and therefore is unknown from the start. No matter how you toggle it, it will remain unknown. To fix this, we initialize WI clock to 0 at first. You can also use a bit if you wish, but we are not doing that here. Second, we handle design reset. Every design must be reset before it can operate. This reset is active high, so we drive it to 1 and after some time we deassert it. If you wish, instead of using time, we can use the clock. For example, we can wait until the clock toggles from 1 to 0, then only we deassert the reset. You can see that I'm using a standalone initial block here. This is to handle initial reset independently. Now separating a reset phase is a very common practice in validation, but you should know there are many other ways to write the same code. It may seem trivial, but it has certain consequences. We'll get to see it later. Now that we've handled clock and reset, let's handle the data. We want to drive one single data like this. At first, all input signals are driven to a known value. Then at the rising clock, we drive one data and along with it, we drive data valid to 1. And at the next clock, we drive the data and the valid back to 0. Now there are several problems with this code. Do you know what they are? First, this code ignores the reset. When we drive data and valid, it is actually at this point and therefore it is still in reset. We need to wait for reset to deassert, so we need to add code like this, then only we can drive the data. If you miss this, one reason is probably because we chose to handle reset separately. If that's the case, you really need to learn to be able to visualize multiple running threads. Another similar problem is that this code handles only the data. It does not handle the register programming. Even though we want to use the default value, we must still drive all control inputs. In this case, we need to drive CRWrite to 0, so that we are not changing conversion size. Else the conversion size may become X and it will impact data conversion. Now here's another way to write the test from start to end in one initial block. First, we initialize all inputs, including driving reset. Then we deassert the reset, and then we drive the data and valid for one cycle. This kind of style is pretty straightforward. It helps you to visualize all of the steps in driving stimulus, but to be frank, only simple tests can be written in this manner. Now let's look at the monitoring outputs. At the end of the day, we want to check the output data against the input data. So we have two variables here, one for the input and another for the output. For the input, we wait for the input data valid, then we can sample the input data. Pay attention that a non-blocking assignment is used here to sample the input data. It generally means always sample the data right before the trigger. Now monitoring the output. We wait for the positive edge of output data valid, then we start to sample the output data bit by bit for the next 8 clock. We combine all of the bits into this result variable, and finally we compare it. If the stimulus matches the result, it passes, else it fails. Now before we proceed further, there is a problem with this code. In fact, a very tricky one to understand. Let's see if you can spot it. The problem is with the non-blocking assignment here. First, never mix non-blocking assignments with blocking assignments. This code is a bit special. You don't really see blocking assignment, but this part can be considered as a blocking assignment. Let's try to understand it step by step. This code is waiting for the output data valid to rise, which is here. This code here basically says for the next 8 clocks, we sample the output data bit by bit. At the 8th clock, we think that it samples the final bit, then it compares stimulus and the result. But that's not what happened because of the non-blocking assignment. At this clock, two things will happen: sampling of the final bit of the output and comparison of the data. The sampling is using non-blocking assignment, and the comparison is generally blocking assignment. According to scheduling semantics, at this clock edge, it will perform the comparison first, then only it will perform the sampling. So even if the design is working fine, the comparison will always fail because the monitor has not finished sampling. One simple thing we can do is to delay the comparison. It's not the best way, but it works. Now let's talk about something more sophisticated. First thing first, this is meant to be a simple test. You have to accept it as is. From that ground, let's see how to make this test better. Number one, this test only handles one stimulus. To handle more than one stimulus, we can use always block. This is an easy one. Next, there are two initial blocks, one for monitoring the input data and one for monitoring the output data. You may ask, why not just one initial block? This is really a choice of one big piece of code or a few smaller pieces. In my experience, one big piece of code is a beginner's choice. If you can reasonably segregate the code, especially when your code is more than 1 page long, I strongly recommend you to. As of now, imagine if I combine these two initial blocks, it does not make much difference, but you will see later what problem it may bring. Another thing is it uses hard-coded size 8. If we want to configure the size and check on it, we need to add code here to read the size before we sample the data. Also, this code only performs check on data. It does not check on any of its protocol. For example, it does not check the output valid. For all we know, it could have gone low at any point of time. There are many other checks we can perform. For example, once an input valid happens, when does output valid go up? Or what happens if there is an invalid input like this? Is this acceptable? If it is, we have to write tests for it. Else we may have to write a check against it. Also, what happens if output valid goes high even though there is no input valid at all? And then there are corner cases. For example, we can send a new input data at this point where previous output data is at its final bit conversion. We can go on and on. Now imagine this is one big piece of code. Adding all these checks would make this code a lot more longer. And then one day the design is updated. For example, output is delayed a few clocks. If you have that one big piece of code, it would be tough to find the right place and update the code. Comparatively, if we segregate all the checks, it would be easier to update. This is one possible example. This assertion checks the relationship between input and output data valid. It says when input valid is up, output valid must be up 1 clock later. If we change the design spec where output is delayed, it's easy to locate this property and fix the assertion, as compared to one big piece of code. Well, that's all for today. Step by step, we'll convert this test into a more comprehensive test bench, and we'll learn various UVM code. Now before we go, don't forget to like, share and subscribe.